Welcome, boys and girls, to our revision for the work we have been doing in matter and materials and also chemical changes. In our previous sessions, we took our time to explain the basic concepts behind the theories of the different sections under materials, matter and materials, and chemical change. And we were using the May-June 2018 past paper as a reference to see, with the information we were explaining, how do we apply it, and in the applications we will be doing, how do we attach the appropriate or necessary interpretations as required by the examination board for our metric examination. So today I'm going to take you through a 2019 May-June past paper, and then we will answer a typical examination questions, where I'll also explain how you approach the question, how you interpret the data which is provided in the question, and also how you apply your background information to answer this question. So if you take, for example, like I'm saying, this is paper 2, May-June 2019. The first question, as you can see, it's about organic molecules, organic chemistry. So we are told that the letters A to F in the table below represent 6 organic compounds. But what I expect you, before you even go into the question, is that once you look at organic molecules like this, it should click in your mind on the nature of the organic molecules you are dealing with, and what is so special about them, and what kind of interpretations you can quickly attach to them before you go into the fine details about the nature of these materials. So, like for example, if you look at this, you can actually see that this is a CH3, and the CH2, and the CH2. Something is happening here, because the way these CH3s are attached are telling you something else. And then if you look at this, you see that there's a special character of a carbon-oxygen double bond that should tell you something unique also. And if you look at this one, it's a straight chain, but there's a carbon-oxygen-hydrogen bond along the way, so that should tell you something also. And what about here? You can see that we've got 2 bromine atoms, and then we've got a straight chain, and on the straight chain we've got a 2 carbon chain attached as a functional group. So those unique functional groups or properties of the organic molecule you can select out should give you a direction on how exactly you are supposed to address this question and make a comparison or a reference to them as they occur like this. So that if you look at the first question, just by studying this, you can see, or we are going to see, that we've already answered most of the questions in this particular section. So if you look at 2.1, it's asking, is compound C saturated or unsaturated? Give a reason for the answer. So where is compound C? There we are. You see the compound C, CH3, CH2, CH3. So meaning that this is a straight chain carbon, but they gave you this deliberately so that you need to show an understanding of the sequence of arrangement of the carbons, and also how they are arranged, how they are bonded. So here it's a 1, 2, 3, 4, 5 carbon chains. So this is CH3, C, CH2, CH3. So here we are. We are saying it goes like this: CH3, CCCH2 CH3 like this. So when we draw our open structure here, we are supposed to show the bonding as it okay. So here we are going to say we've got a carbon, a third carbon, a fourth carbon, and a fifth carbon. So the first carbon has got 3 hydrogens like this, and then the second one has got 9, and the third one has got 9, and he's got H, and this one has got H there, H, and H. So this is happy, it has got 8 electrons. This one is happy, it has got 8 electrons, but this one is not. It only has got 4 electrons. So how does it get the other 4 electrons so that it will have an octet? So if we bring another bond to make it a double bond, so you see that this carbon will have 2, 4, 6. So it's still missing 2 electrons, while this one is also having 2, 4, 6. It's still missing 2 electrons. So what it means is let's bring a third bond. So this becomes 2, 4, 6, 8. 2, 4, 6, 8. So these two are now happy in terms of the octet rule with a triple bond there, and this one is happy already as it is. So you can actually see that this is an alkyne, and this alkyne has got a triple bond right in the middle there. And since it is 1, 2, 3, 4, 5, so it's going to be a pen 2 ine, or we can say 2 pentyne, like that. Is with a triple bond. Okay. So the reason here we are saying compound C is unsaturated, and the reason is that there is a triple bond between carbon number 2 and number 3. Okay. So they're saying write down the letter that represents each of the following: an ester. How do we know that this is an ester? So an ester, we know that it has got an oxygen bond, a carbon oxygen bond right in the middle of the carbon chain. So if you look at this, there is no oxygen there. On B, there is one, and even the name butyl propanoate, and it tells you that this is if you look at this one, this is an aldehyde, but D, which is butyl propanoate, it cannot be an ester because a propanoate, it is an ester because it has got a carbon oxygen carbon bond. So we know that esters, they've got the following structure. They've got a characteristic bond of a carbon, and then like that, and that. That's an ester. So this is an ester bond. So if we look at this is not an ester, this is an ether, while this one is an ester. So to answer our question here, a letter that represents an ester is a letter D, and then a functional isomer of butanol. So like this one is a ketone, because a ketone has got a carbon oxygen bond in the middle of the chain, but when the carbon oxygen bond is on the far ends, it will give you an aldehyde. So a ketone is going to be something like this, where we are going to have a functional isomer of butanol. There it is. Okay. So in this case, we are saying it's an isomer because the oxygen has been rearranged. One would argue and say, but we are saying this is butanol, but the carbon oxygen bond is not on the far end of the carbon chain. So this is how we make a representation of that phenomenon. We are saying an aldehyde has got a carbon oxygen bond on the far end of the chain, like that, but a ketone has got a carbon oxygen bond in the middle of the chain. So when we are talking about isomers, when we are talking about isomers, we are saying that isomers, you would have moved around a functional group. So what we are saying is that where this oxygen was on the last carbon as a butanol, this oxygen has been moved to the next carbon atom to give us this. So now this is no longer a butanol, but it's a butanon, a ketone, which is an isomer of the butanol. Okay. So for 1 mark, you see that a letter B is a functional isomer of butanol. A compound with the general formula CnH2n-2. If you remember in one of our sessions, we agreed that these homologous general formulas, they tell us which group of materials is this. So if you remember very well, here we are talking about C2H2n-2. When we started, we talked about C2H2n plus 2, and we say this is for alkanes. While for alkenes, it's C2H2n only. So we are saying this is alkenes, while this is alkanes. So this becomes alkynes. Okay. So C2H2n-2. So with alkynes, we expect a triple bond, while in an alkane, it's a saturated carbon chain. In an alkene, is a double bond. Okay. So here we are. To answer this question, we're saying write down a letter that represents each of the following a compound with the general formula CnH2n-2. So that will bring us back to C again, because this is where we've got a triple bond in alkyne. Okay. For 1 mark. Then a compound used as a reactant in the preparation of compound D. Okay. This is compound D, which is a butyl propanoate. So we know that an ester is prepared from a carboxylic acid and an alcohol. So this is butyl, so it means that something should come from a butane, butanol, or a butane. So if you look at all these compounds, this is 1, 2, 3, 4, this is butanol, which can be used to make butyl propanoate. So yes, letter E will answer 2.2.4. So he's saying write down the structural formula of the functional group of compound C. The structural formula of the functional group of compound C. It looks like we had already answered this part of the question. If we go back like this, I think I rubbed it off. But anyway, I started train slash. We can still represent it. We are saying that compound C. If you look at compound C, that's the one which is with a triple bond. So if we are to draw the functional group of compound C, it's going to be something like this. When we are saying it's going to be a carbon, a triple bond there, and another carbon like that. So we are going to have a CH3 there, a CH2, CH3. Okay. So the functional groups here we've got a methyl as a functional group, and we also have an ethyl as a functional group. So in other words, we can rewrite this whole thing like this, and then write methyl there and ethyl over there like that. So these are the functional groups. So any one of the functional groups are going to put down there is acceptable. Okay. Compound D. Define the structural formula of compound D. If you look at compound D, there it is. So it's a butyl propanoate. So there are two functional groups we are putting together here. A butyl and then a propanoate. Propane is got it's a 3 carbon chain. So if we are to write this, we are going to have a butyl, which is going to be C 1, 2, 3, 4. Okay, so this is going to be H, like that. And then here we're going to have a carbon oxygen bond, and then a carbon over there, and a carbon double bond, a carbon and a carbon. So this is a 3 carbon chain. So it's going to be H over there, H there, and H and H and H. Okay, and here and H and then H like that. So this becomes butyl propanoate. Okay, so this is the butyl part, and this is the propanoate part. Okay, so there you have it, and the functional group of interest is this part, which shows that this is a ester. Okay. And then on top of that, so you see that we also know a chain isomer of compound A. A chain isomer of compound A. So if you look at A, it has got a CH3, and 2 carbons like this on a chain like that. So if we are to make this a chain molecule, it means that it would have undergone isomerism. So for that reason, you'll see that F represents very well a chain isomer of compound A. So yes, right. So actually, if we need to draw the structure, let's see how we are going to draw it, the chain isomer. So here we are saying this is a carbon with a H2, and then CH3 and CH3. So in other words, this is a branched molecule where we have got 1.2 dimethyl ethane. Okay, so if I write the name, it will also help you to see how the isomer has changed. So this is going to be 1.2 dimethyl ethane. Okay, now if I'm to write this as a chain isomer, so it's going to be CH3, CH2, CH2, and CH3 like this. So this is going to be this. So this is going to be a simple straight chain butane. So do you see the difference? This is a 1.2 dimethyl ethane, while this is butane. So you can see that this is a branched molecule, while this is a straight chain. Okay. So just for 2 marks, you are supposed to be able to draw that as quickly as possible. Now write down the IUPAC name of compound F. So we know that for us to write names of compounds, we need to study the molecule in detail. So what we are going to pick up here is that we need to first identify the longest chain. So the longest chain here, there are 2 ways about it. We can count how many carbons we can count continuously. So like in this case, this can be 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6, 7. So our longest chain is going to have a 7 carbon chain. So with 7 carbons, it's going to be a heptane. Okay, like that. So since it is a heptane, let's see the functional groups that we are going to have. So if we identify 7 is our longest chain. Then we can say, so this becomes a methyl, a bromine, and a bromine. So where are they? So we are going to have our first bromine on carbon number 2, while our methyl is on carbon number 3. So obviously we are going to take the bromine as the functional group of priority. So we're going to have bromine on number 2, a bromine on number 3, and then a methyl on number 1, 2, 3, 4, 5, on number 5. So for that reason, we also arrange them according to alphabetical order. Which one comes first? Bromo. So this whole molecule is going to be 2.3 dibromo. It's going to be dibromo, and then our methyl is on carbon number 5, so it's going to be 5-methyl heptane. Okay, so because the IUPAC gives us some rules on how to name compounds, the first one being that identify the longest chain, and then identify the functional groups, and then identify the order of arrangement, and then from there you identify which ones comes first according to the alphabetical order. Okay, so yes, for 3 marks we gave the IUPAC name of compound F as 2.3 dibromo 5-methyl heptane. Okay, so we are saying balanced, write down the balanced equation using molecular formula for the complete combustion of A. If you look at A, here it is. So we are going to use here molecular formula, not structural formulas. Because molecular formula will simply tell us what elements are in the molecule. Whether they are arranged in a straight chain or in branched chains is not going to affect how they are going to undergo combustion, because at the end of the day, all the materials are going to burn down. So what is important here is just for you to show a clear representation of what is happening. So we saw that compound A, it's a 4-carbon chain of a saturated hydrocarbon. So we can write it down as C4H10, like that. And then if it is going to undergo combustion, it means that it's reacting with oxygen, it's burning. And when it is burning, we are going to produce carbon dioxide plus H2O. Okay. So let's assign state symbols, understand that condition. So we are saying this is a gas, this is a gas, carbon dioxide is a gas, and this is going to be a liquid. So since we've got 4 carbons here, let's make them 4 here. And since we've got 10 hydrogens, let's make 5 water molecules. So now how many oxygens do we need? So this is 4 times 2, which is 8. 8 plus 5, which is 13. So we are going to write 13 there over 2 to give us a result. So now to get rid of this fraction, let's multiply everything by 2. So it's going to give us 2C4H10, a gas, reacting with 13 oxygens, a gas, to give us 8 carbon dioxide gas, like this, plus 10 water molecules and liquid. So there we have it. This is going to be your your final answer which you can present. Yes, this is acceptable, this is correct and acceptable, fine, but we know the challenge of some of us not being able to comprehend what this representation is all about. So it's always advisable to present your balanced equation in a simple and straightforward manner like this. Okay. So boys and girls, for all that, 17 marks. Is there any approach which was not clear enough for you to understand what is happening where and when here? As far as I'm concerned, with the previous explanations we attached to this concept, it's very easy to approach these types of examination questions and explain and interpret the data you are given and make appropriate applications as you are answering this question. Okay. Now the next part, let's move quickly to question 3, and as you can see, it has got only 12 marks. So you shouldn't struggle much, especially if you understand what's happening here, and you can obviously see that it's still talking about organic molecules. So let's study the organic molecules and see what exactly are we being asked here. So if you look at this, they're saying that 3 compounds are used to investigate one of the factors that influences boiling point. We agree that boiling point is the temperature at which a liquid boils, changes to a vapor. So here you've got a compound, butane, and then the molecular mass is 58, boiling point is minus 0.5. So the fact that this is just below 0, it means that it's a gas at room temperature. Propanol, molecular mass of 60, imagine, just 2 more grams, it is got a boiling point of 98. So ethanoic acid, same molecular mass, but it has got a boiling point of 118. So if you study these compounds before you even attempt to answer the question, something should ring into your mind that these molecules have got different functional groups, they've got different carbon chains, and also the different arrangement of those functional groups in their respective molecules. So what comes into effect as a result of all those differences from your background information is that intermolecular forces, as a result of both their functional groups and their molecular masses, are affecting their boiling point. So let's see how do we answer this question. You're seeing that in one investigation, the boiling points of compound B and compound C are compared. Okay. Is this a fair investigation? Write down yes or no and refer to the data in the table and give a reason for the answer. Can we say these materials can be compared? Let's look at the data we have here. They both have the same molecular mass, but we do have they do not have the same carbon chain length, and also they do not have the same functional groups in their molecules. So you'll see that having the same molecular mass alone does not make it fair for the investigation to compare the 2 molecules. So we are going to notice that it's not going to be, our answer here is going to be no, it's not. Why? Because in as much as they have the same molecular mass, they do not have the same carbon chain, they don't have the same functional groups that influence the intermolecular forces that are at play in the molecule. So all those, they outweigh the existence of the same molecular mass of the molecule. Okay. So here, if we are to write down the independent variable for this investigation, you'll see that the independent variable is molecular mass. Okay. Which one of the following compounds, A, B, or C, has the highest vapor pressure? And give you a reason for the answer. 2 marks. Listen, boys and girls, we are saying vapor pressure here. In other words, we are saying a substance with molecules that can quickly turn into vapor will obviously have the highest vapor pressure. So a substance that has got a lowest boiling point, it means that it quickly turns from a liquid to a gas, and as more molecules turn into a gas, those gaseous molecules increase the vapor pressure of the molecule. Okay, so if you compare these A, B, or C, you will see that A is the lowest boiling point, which is actually below 0 degrees Celsius, meaning that even at ordinary room temperature or standard temperature, it is a gas already. So what it means is that A will have the highest vapor pressure. Okay. So referring to the intermolecular forces present in each compound and fully explain the trend in boiling points as shown in table above 5 now. Boys and girls, look at this. There are 5 marks here, meaning that there are a lot of things which you have to represent in terms of justifying what you are going to attach as an explanation of explaining the trends in the boiling points which we are observing here. So what I'm going to do, I'm going to draw the structures of butane, propane, 1R, and ethanoic acid, and then we see how things are changing. So we are saying our butane has got 4 carbons in its chain like this. So if we are to see how the hydrogens are arranged there, it's going to be like that, like that, and that. Okay, the next one is propane 1O. So if we are going to have propane, it's 3 carbons in its chain. 1O, it means that the OH is on carbon number 1, so it's going to be like this. Excuse me. And this, and that, like that. Okay. So, and then the third one is going to be ethanoic acid. So, ethanoic acid is like this. HC. And then here we've got O, and then OH. So if we compare these molecules, I want you to take note of this molecule, compare it to that, and compare it to this, and see how our things going to be like. So if we compare so this is going to be A, that's compound A, and then this is compound B, and this is compound C. So remember, the question is saying, referring to the intermolecular forces present in each compound and fully explain the trend in boiling points as shown in the above. So we are going to notice that this is going to be in A, there are no any special functional groups other than the simple carbon hydrogen bonds and a simple straight chain carbon. So meaning that the intermolecular forces we are going to have here are going to be those weak van der Waals forces. Why are we saying they are weak? Because the carbon chains have got 4 carbons, and it has got a very low surface area on which the intermolecular forces are going to act between the molecules. And another issue also is that it has got a very small molecular mass, meaning that it has got a very small density, and also that weakens the van der Waals forces which are existing in the molecule. That's why its boiling point is minus 0.5 degrees. But if you come to B, this is propanol. What do we know about molecules that contain a highly electronegative species, or a functional group or atom in its molecule? So like in this case, the propanol has got oxygen in its molecule. And we know that when oxygen is attached in a molecule, it has got a very high electronegativity. So firstly, it is inducing a dipole bond between the carbon and oxygen, meaning that this carbon is partially positive while the oxygen is partially negative. So the dipole moment in the molecule itself will result in the induction of another dipole moment in the next molecule. So we are going to have, in addition to the van der Waals forces, we are going to have dipole-dipole interactions that is going to increase the intermolecular forces acting in there. Not only that, in each propanol molecule, there is an OH, an oxygen like this, and a hydrogen like this. So on the next propanol molecule, we're going to see that the hydrogen is going to be bonded to the oxygen of the next door molecule in a hydrogen bond. And then the hydrogen bond is formed from a hydrogen attaching to the lone pair of electrons of the next door oxygen molecule in the OH group of the propanol. So on top of the van der Waals forces, we've got dipole-dipole interactions, and then also have hydrogen bonds. So that's why it increases the boiling point to 98 degrees, besides the fact that from the butanol, the propanol, from the butane, the propanol has got a 1 carbon short in the carbon chain, but still has got an extremely high and a reasonably high boiling point. Now if we go to compound C, we can actually see that the boiling point is actually even more higher than that of propanol, because the hydrogen bonding which is going to take place in this molecule is going to take place on 3 different places, or even more. So we can have a hydrogen bond forming here, a hydrogen bond forming on this hydrogen over there, a hydrogen bond forming on this oxygen, and another hydrogen bond. So apart from the simple van der Waals forces, we've got multiple hydrogen bonds forming on the carboxylic functional group. So that's why it increases the boiling point of ethanoic acid to 118 degrees as compared to that of propanol, which has got fewer hydrogen bonds, as compared to that of butane, which does not have any hydrogen bonds completely. Okay. So the next question is saying, which compound, butane 1O or propane 1O, has the higher boiling point, and give a reason for your answer. So we are now comparing 2 alcohols, but you can tell that the only difference here, they are all alcohols, meaning that the OHs are all on the carbon number 1. So the only difference here is the carbon chain. So if I'm to show you how this is going to happen, so a butane 1O is going to be something like this. I'll put an OH over there, and you know that all these are hydrogens. And then a propane 1O is going to be like this. 1, 2, 3. And then we've got an OH there, and you see that all these are hydrogens. Okay. So the only difference here is the carbon chain. So this is longer by 1 carbon and this is shorter. So what effect does it have? the molecular mass of butanol is going to be larger. So if you take a look at it, this is going to be 12 times 4, that's 48. 48 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it gives us 58. 58 plus 16, that will give you 74. So this is going to have a molecular mass of 74 grams. Well, this one is what? 36, that's 7, 38, 39, 40, 41, 42, 40, 41, 42, 43, plus 16, it will give you 62, right? So it's going to be a mass of 62 grams. So for that reason, you'll see that this is more dense and this is less dense. And because of the longer chain, there are going to be more surfaces of interaction with the intermolecular forces and as compared to this. So this butane or butane 1O is going to have a higher boiling point than propane 1O. Okay. So for that reason, you'll see that just for 2 marks, we can safely conclude that the butanol has got the highest boiling point for those 2 reasons we have highlighted there. Okay. So boys and girls, I want to believe that with this, we can quickly go through question 4, also the organic, because it's going through the organic molecules, and then when we meet next, we'll talk about the rates of reaction. So if you look at question 4, it's saying that the balanced equation for a polymerization reaction is shown below. So we are having an alkene forming a polymer. So this alkene is ethane and it's going to form a polyethane. Okay, so they are saying write down the type of polymerization reaction represented in this equation. So you can see that here you are simply adding across the double bonds and then extending the chain for 1 mark. So IUPAC, name of the monomer. Monomer is the 1 unit from which the polymer is going to be made from. So it's going to be a ethene. And then the polymer is going to be polyethane. See, just for 1 mark, 1 mark, 1 mark. So this is very simple and straightforward. Okay. But the second question is saying propane 1O undergoes 2 different reactions as shown in the diagram below. So you can see that propanol reacting with hydrochloric acid, it forms compound Y. And then it reacts with concentrated sulfuric acid, it forms compound X. And it reacts with water and sulfuric acid, it forms compound Z. So how are we supposed to predict what is happening here? From our background information, we should know what purpose does these reacting conditions do. So if we are to answer this question, you see for 1 mark, you're saying type of reaction represented by reaction 2. So you will see that this reaction 2 is going to be dehydration, because this is concentrated sulfuric acid. So the propanol is going to lose a water molecule, and then when it loses a water molecule, it's going to form a double bond on one of the carbons, a carbon single bond. So it's going to be propene. Okay. So, and we know all the time that the moment we see concentrated sulfuric acid, is going to be dehydration. So the dehydration process is going to take place by means of an elimination reaction. And what are we eliminating? A water molecule. It's going to be removed, where the OH is removed on one of the carbons and the next door hydrogen is removed on the other carbon to form a carbon-carbon double bond in alkene. Okay. So they are saying the IUPAC name of the compound O. Since this is propane 1O, it's going to be propene or 1 propene or prop 1 in. Any of those 3 names are acceptable. And then the structural formula of compound Y. Now this is very simple, because what we know here is that the OH is being replaced by the chlorine in this reaction. So the structural formula of this compound is going to be, so remember initially it was propane 1O, so it's going to be, if it was propane 1O like this, and that if we take this through substitution, where we replace the OH with a chlorine, it's going to be a chloropropane like this. And then it's going to be a chlorine there, and H, all these are hydrogen. So we have replaced the OH with a chlorine to change it from propanol, propane 1O to 1-chloropropane. Okay. And then this last part of this question is saying the type of reaction represented by reaction 3. Reaction 3, we know that we call this acid catalyzed hydration of alkenes. So we are adding water across a carbon-carbon double bond. So remember initially during this process, elimination took place or dehydration, and you ended up forming a double bond on a carbon-carbon double bond to form propene or 1-propene. Okay, and now we are adding the water molecule back across the double bond. So in other words, we can say it's an addition reaction or it's a hydration reaction, and the specific name of that reaction is called acid catalyzed hydration of alkene. So we are going to have the IUPAC name of the compound being a 2-propanol or prop-2-nol. So if I'm to write it down, it's going to be, so remember it was something like this initially, and then we are adding water across it through a acid catalyzed hydration. So this is going to change to be, so if look at this is how it was looking like, and then if we add water, so it's going to, using Markovnikov's rule, the hydrogen is going to attach here, and then the OH is going to attach there. So we are going to have like this. So we call this propane. So for 2 marks, you give it a technical name like that. Okay. So when we meet next time, boys and girls, we are going to move on to the interesting part of electrochemistry. Okay. Thank you very much.